Well, good morning, everybody, and welcome from Camarillo, California, to this webinar on circuit models for magnetics. We've got lots of people still streaming into the room, so welcome from everybody all around the world. I think at least 17 different countries are here for this, so we're very pleased that you're all here. Please, when you're on there, please look on your control screen for the GoToWebinar, and you should see some handouts. You can find the slide handouts, so you can follow along and make notes on your slides if you want to. So you will find that available. And there's some other collateral material there that you can download and read at your leisure as well. My name is Ridley. Been doing power electronics since a long time ago, 1980 basically. I've been involved in magnetics, circuit design, topologies, control was really my first love in power electronics because I studied a lot of that at school. And we've been doing these webinars now for the past about 10 years, I think, and teaching for the last 20 years. And we'll tell you a little bit more about our teaching events at the end of the webinar. So please stay around for that because we also have some important information there for you as well. At any time, you can ask questions. If they're technical questions, some of our staff here, Chandler Ridley, Denise Ridley, will help answer those. If they're about the webinar, sound should be okay for everybody. Some of you will have issues with that. It's probably at your end. It's definitely at your end because it's fine for everybody else. So you can ask questions anytime. I will, if there are important questions that need to be answered right away, because there's a lot to be asking the same question, I will try and stop to answer those. Otherwise, we'll reserve the questions for the end of the webinar. So we'll see how that goes. But some of you will have them have them answers as we go through, hopefully. And one question there, obviously very important, is that a Gibson guitar at the back? No, it's not. It's a it's a different guitar. All right, so welcome. This is about practical circuit models for advanced magnetics. And this is something we've been working on for quite a few years now and thinking about really for a long time through various conversations with people in the industry, various work, various observations that we've seen in power supplies over the years where, as many of you know, one thing that always happens is the magnetics are too hot. And it's difficult to see that coming when you initially do your design unless you do some very in-depth analysis. And as we're going to see from this webinar as well, there's some measurements that need to be made as well, and not just in-circuit measurements, because you need to figure out where the losses are coming from. But we're going to focus mainly here on not so much the practical building of magnetics. You will find some of that in our early webinars, but in the SPICE modeling of the magnetics, we can do a lot more than most people are attempting these days, especially magnetics companies. This has not been a focus for them. And after going through this particular exercise for a specific inductor, I think I understand why they have stayed away from the SPICE models of magnetics, because they've been quite unsatisfactory, to be honest, even the ones that we generated in the process here. So I can see why they have drifted into a different direction, but they've also taken the first step to generating decent models. So we'll talk about what that first step really is. So some of the people involved in this, it's not just us, just me here at Ridley Engineering. We have all our staff here, of course, at Ridley Engineering, but some important people I want to mention. One is Mr. Art Nace, who's been programming part of Ridley Works, and especially the link to LTspice for us for quite a few years now. And what that does is it is it makes the transition from our design program into LTspice modeling completely seamless. It just takes one click of one button and you've generated all the models that you're going to see in this webinar. And that's really important. If it's a painful process to move from one software into another, you know, quite honestly, if you're a working engineer, you're not going to do it. And then that is what, you know, our work here is mostly about, is helping the working engineer. Also to mention Dr. Vache Vorperian. Many of you, of course, are familiar with him. You know, probably his greatest contribution to our field is the PWM switch model, which saved us all from state space averaging many, many years ago. And Vache and I started conversations on core loss models back in the 1980s. Some of you may remember when the Mandelbrot sets came out on fractals back in the 1980s. We all had little PCs at the university then, and many of us rushed off, you know, and Vache guided us on this into plot some of the Mandelbrot sets and the fractal modeling pictures that were very popular at that time. But while lots of us were trying to do those plottings of those interesting pictures, Vache picked up that fractals in general had a very important role in modeling, you know, fractional frequency response terms that he applied to core loss way back in the 1980s. I think he was probably the first one to do that. And we're going to see in some of our measurements, and we're going to see in the predictions of proximity loss, that these fractional terms in the frequency domain are very important, and we need fractal models or partial fractal models to produce that. So anyway, thanks to Vache, and always ongoing discussions with him about how to get things done in this field. Qichen Yang was our summer intern for 6 weeks a few years ago, and he solved the math for us for 5th and 7th order models. I still don't know quite how he did it. It's in our program Ridley works at this point. I know enough to go in there and modify it when it doesn't converge properly. But 5th and 7th order mathematics is beyond my knowledge. So unfortunately, we had Dr. Yang who helped us out with that. And then also Dr. Shilpa Mati, who was also one of our interns over the same summer. She spent many weeks doing a horrible job, which is collecting core loss data. You know, the point of that was that so we don't have to anymore. So I no longer go to the core loss charts for the materials we use, because she collected the data that we needed, and of course that got loaded into our software. So thanks to all these people, and there are many more as well that I will mention as we go through, hopefully. Things to feel good about magnetics. Most people are terrified of magnetics. They're worried that they don't understand it. They go into a session, maybe at APEC or any conference, or they read transactions papers on it, and by the time they've read the papers, they understand it even less than when they first went into digging into it. And you know, part of the problem is any self-respecting magnetics paper starts with a triple integral, just to show that you're serious, and it moves on from there. And in that process, people get it becomes very obscured that the process of building and testing and making magnetics is actually a very, very simple process. And of course, that's something that we teach in our workshop. But don't feel bad that you don't understand. Richard Feynman didn't know magnetics, how it works either. And this is a great video to watch. It's a little YouTube video where somebody is asking him about magnets and what's going on and what happens. And you listen through the 7-minute video here, and his conclusion in the end is basically, you know, nobody knows what's going on at all. We can just find a way to describe it in mathematical language. And that also came up last week on somebody posting in LinkedIn. Don't know if this person is here at the webinar, but somebody works in integrated magnetics. Who said we don't understand the universe itself. The best we can do is make a model of it and then try to understand that. So if you substitute universe for magnetics, nobody really understands magnetics, what's going on, any more than Richard Feynman did. But what we have is models, and we work hard to understand those models so we can build things with the models. And that's really a big point of what we're doing in this webinar. Next piece of good news for you. It's late in the evening for many of you, past midnight for others, and early in the morning for people in California. There are 0 equations in this webinar. I got to revise that. There are some equations, but they're not mine. Okay, they came from one of the semiconductor manufacturers. And I found over the years that if you do a presentation and you include an equation, any engineer in the room then has to understand exactly what that equation means before he can move on to understanding what you're talking about. That doesn't mean that we have 0 equations involved in our design process. Of course we do. Every equation you need is in our Ridley Works software. Many of you already have it. And then the good news is, more good news, at the end of the webinar, we'll let you know how you can get a free copy. And then you'll have every equation you're going to need for, you know, building the models that we have. You'll have the circuit models. You'll have the actual circuits that are included with our distribution now. So you can rerun all the examples that we're doing here in this webinar. Plus, if you attended our, you know, filter feed forward webinar, you know, we have those circuits in there as well. So that's good news as well. And if you have questions, you know, lots of questions about equations, there's a tendency in our field to, you know, just become too academic and to drift into the world of solving very difficult equations and then missing the point of what we're trying to do, which is power conversion. So let's start here. Let's talk about semiconductor models. This is a part from EPC. This is a GaN part. Really, really tiny, 0.8 millimeters by 1 millimeter, so it's an extremely small part, but it's capable of very low on resistance in these tiny parts. And some of you I know are experimenting with these. You know, the hardest part of the experiment is, of course, is dealing with the very small package sizes and getting them into your circuits and soldering them correctly. But we're not going to talk about that. Let's just say that if you have a semiconductor part, you want to get into the market and you want to sell to some of the big companies like Apple or Ford or whoever, of course you need a schematic element for it. It's just a regular MOSFET looking here, but this is what shows up in LTspice. And then the first question that the big company is going to ask you is like, okay, where's the SPICE model? And even though you've only just finished fabricating your part and making it, you better provide this. Otherwise, nobody is going to try it. They need to put it into the circuit and they need to see what it's doing for them before they get involved in a new technology. Obviously, there's going to be an investment of time, learning. They've got to get over the risk, reliability, and so on. But at least we should be able to run the simulation and see how this part might help us. So semiconductor companies do this really well. They're very complex models here. Variable capacitances, gate to drain, gate to source, and so on. And all the different gains, you know, you can add in as many parasitics as you want, but the models are there and they have to be there. Semiconductors are quite complex. Magnetics really aren't. So here's an example of a coilcraft inductor. This is the one we're going to be kind of digging into in this webinar. And the reason we chose this particular one, you can see this hopefully circuit board here. It's had the magnetics removed, but this is like a 1 kilowatt converter. And here's the magnetic that goes on it. And there's 2 of these on the circuit board. We've pulled them off to dissect them actually and do some analysis on them. But there's 2 on this circuit board. And I don't know how we came by the circuit board, but we were investigating it for control issues. But it's a 960 watt converter. It's a buck boost. And everything except the magnetics is really, really tiny. In fact, one inductor is bigger than all the rest of the semiconductors and passive components combined. So maybe we'll shed a little light at the end of the webinar of how that might be reduced if we have time. But there's the inductor, and then we have options of how we're going to model. Now, magnetics companies give you very little in terms of a splice model. They give you the DC resistance, and they give you, of course, the value of the inductance. So that's what your initial start is on trying to model this inductor. You can get a little bit more complex. Some of you out there are familiar with, proximity losses, i.e. the resistance changes with frequency. So you can substitute, you can add an additional resistance in here, which results from Dalls equation. Of course, you can use Dalls equation, which is a big step in accuracy, and then you can do refined Dalls, Bessel functions, anything you want to do. You can take it as complex as you like. So that's level 1 model, which is basically all you have from the data sheet. Level 2 model adds some AC resistance, and we're going to go through that. Level 3 model will then put a core loss circuit across the core, and this is a voltage-driven device. It's driven by the voltage on the inductor because it's the delta B that drives core loss. So it's not in series with the inductor, it's in parallel with the inductor. So that's core loss and the calculated proximity. And then what we're going to find in this webinar is that this model, even though it's more complex, more complete, doesn't cut it for this particular case. And we have to go in and we have to actually measure the AC resistance of this inductor in order to get a good fit versus the data for the particular inductor. So that's where we're going to go. We're going to look at these 4 different models, come up with the final model, and then see how well that does versus the data that we get from manufacturer doing a very large amount of testing these days. So the testing side is really good in terms of the dissipation. Not sure how they did it, thermally or whatever they used, but can we put a model in there to match reality? So here we are. Here's magnetics model 1. And here is a simple circuit that we're going to put it into. I've kept the circuit simple, just, so we don't get confused. Okay, full bridges, half bridges, LLCs, and so on. Let's start with the buck converter, because we have a lot of data for the buck converter from the manufacturers or the boost or any of the basic DC to DCs. And what is our objective? Our objective is that when we run a SPICE simulation on this circuit, we should be able to click on any element and find out what its dissipation is going to be. And that is true of the switches and the diodes, the capacitors, any of the passive elements here, even the control chip have models that will tell you the dissipation. And the one glaring omission is the magnetics. Nobody expects that the simulation of magnetics loss is going to be anywhere close to what you really see. And for some reason in our industry, even though we're completely magnetic centric at this point, the remaining problems are in the magnetics. Semiconductors are solved. It's a solved problem. We have better switches than, quite honestly, we know what to do with at this point. The investment there has been enormous. But for some reason in this field, we accept that we don't expect the magnetics models to work. So hopefully we can change that perception. Here's a little simulation of the circuit just to show you where we're operating. We deliberately chose a design here that would have substantial ripple in the inductor because we want to drive the core hard and we want to drive the AC resistance hard. So if we were just passing DC through this inductor, dissipation predictions would be just perfect. If you're passing lots of AC current through here, we're going to see that we're going to run into problems. So we got almost 5 amps peak to peak of AC here, and then a 10 amp DC current for this particular circuit. Later on, when we come up with a full model, I will actually run the LTspice simulations for you. Okay, so that's where we're going. This is model number 1. And here's the simulation results. So we're working with this Coilcraft part now, and congratulations to Coilcraft and the other manufacturers for doing a really good job of predicting all the losses under different conditions. They've all got their own particular little model for running the inductors, and you have to go to their specific design page on their web. Everyone's different, so you can't compare a Coilcraft versus a Worth versus Coltronic versus anybody else's. They all have their own very specific program that you can go into to look at the dissipations here. So here we can see what the DC to DC optimizer from Coilcraft comes in with. And here we can see what the simulation of the DC model comes up with. And it's pretty bad. We've got 2 watts of loss here, and here we've got maybe 0.2 watts. So it's a 10-to-1 difference of the DC model versus the actual model. So why don't we just use this and stay with this? Well, that's the trend in the industry, but imagine now if you took every circuit element here, and of course we're going to have much bigger, more complex circuits than this. If for every circuit element, every manufacturer, you had to go to a very specific program just to find the dissipation in that one part, how ridiculous would that be? What we want is a SPICE model that gives us one uniform platform, so everybody's part can be thrown in there. You can compare one part versus another, and you don't have to go to 100 different websites to see how the different parts are doing. So that's our goal. So this is what we're doing. Sorry. Yeah, there's two sets of graphs here that you can generate on the Coilcraft page. This one fixes the frequency at 200 kilohertz and varies 80 volts to 130 volts input. Of course, 130 volts input, you can have a higher ripple in the inductor, so you can see the losses climbing here. And then the second chart on this page is fixing the voltage at 130 volts. So go for the peak voltage where the dissipation is highest, and then vary the frequency all the way down, in this case, from 140 kilohertz up to 300 kilohertz. And again, you see that the LTspice simulation is a pretty dismal performance compared to the actual losses that you're going to see. Interesting thing to know, some people think if they're new to magnetics, as the frequency goes up, the magnetic losses get worse. They don't, because you have to consider these in the circuit. And in the circuit, when you're running at a higher frequency, the ripple current is lower, the delta B is lower. So even though if you were driving the delta B and the ripple the same, the losses would go up. You're not driving them the same. So as you change the conditions here, especially dropping down the lower frequency, that's when the dissipation starts climbing through this particular inductor. But again, it's a big miss. On the PDF download that you have, if you click on any of these references here, it will take you to the page so you can run this yourself. All right, so that didn't do a very good job. Now we say, okay, let's do Dalls equations on this. Let's go solve the proximity loss, because we know when we look at the coil that's in here, this is the coil extracted from the inductor. These are very wide traces, and at high frequencies, the current just flows towards the innermost part of this. So we're going to see an increase in AC resistance fairly early on these parts. So now we're enhancing our model, DC, DC, AC resistance. And plotting it 2 ways here, linear plot, and we're going to do a logarithmic plot as well. And you can see that the resistance AC is much, much higher at 100 kilohertz, and 200 kilohertz is here. So we start out with 2 milliohms, and we're ending up with about 50 milliohms here. So we've increased the AC resistance by a factor of 30 at that point. That's a big change, big change. And you see a curve on the linear plot here. And then I remember having a conversation with Dr. Vorperian a long time ago. He says, well, plot it logarithmic, you'll learn something. And you absolutely do when you do this. So if we plot it logarithmically, same data, now we can see this very nice fixed slope on the resistance here. So this is a 1/2 slope, and the 1/2 slope means that the resistance is increasing at the square root of the frequency. And some of you may know that the skin depth goes down with the square root of the frequency. Hence, the resistance is going up at that point. Interesting for this particular structure, how early it starts doing this. Even down at one kilohertz, we've already bumped up the resistance quite a bit. So it goes all the way down to maybe 100 hertz. And again, that's because the turns are so wide. So it doesn't look like it's going to be that great for its application here, but in reality, we normally don't have a lot of AC excitation on this part. So it's probably still going to be okay for a buck converter where the ripple is relatively low. And in the, the application from linear technology, that, 960 watt application, it's fine, but it's a big part at the same time. So there's Dalls' equation. And all these graphs come right out of Ridley Works, okay? You can get a copy of Ridley Works. We'll explain how to do that later on. You can solve Dalls' equations yourself, which is a couple of months out of your life to get it solidly done. Or you've already done that and you solve this in a spreadsheet yourself for about, I would say about 0.1% of the industry have actually done that. It's not easy. It's not easy, unless that's your thing. How do we do? Let's put Dalls' equations and the loss plots. Well, this was the DC resistance. This is with Dalls' AC. This is reality. It's like, oops, well, maybe we doubled the dissipation out here, but we're still a long, long way away from matching the real losses. So I talk to magnetics companies quite a bit about Dalls' equations and losses, and most of them tell me that, no, we don't do that. And maybe this is why, because it misses so badly. It's like, well, what's the point doing all that difficult analysis if in the real part you're going to miss by this much anyway? So that's that bit. Now we'll add the core loss. Okay, and by the way, if you want to see more details on how we do this core loss, I can't do it in this webinar because it takes too long to go through all the details of that. Go read, go watch this magnetics core loss webinar. Again, everything comes out of our software program you can use. So we can add the core loss to the model. And here we go, we're getting a little better at this point. So here's DC resistance, no core loss. AC resistance, no core loss. Now Dalls' AC resistance plus the core loss. And now we're getting up to about 1/2 of the actual losses. Okay. What is my core loss model? Well, we presented this before. It's not nobody else has a model quite like ours. We've done something different. We've done something which I consider intuitive. And we've also done something that would never get accepted in an IEEE conference or transactions. But that's not my goal these days. It works when we get to the final results. You see that the model we have that works. And I'm not going to obsess over how we make this more and more and more accurate when core losses move so much from one part to another anyway. That there's only so much time you should invest in that versus, hey, here's a model that's pretty practical. It's quite easy to simulate. It's not mathematically complex. It's very easy for us to generate, but it's still doing a rotten job. So we're not too happy about that. So there it is also on this, but hey, at least we're getting the effect here. The loss is coming up versus the blue curve it's here. So we know it's climbing in this region. It's climbing much faster than just AC. The AC resistance is telling us, but it's still not good enough. It's still not good enough. Now we know that our core loss model is pretty good because when we run, we've been using it for 6-7 years now, and it's a very close result compared to the core loss charts, and it gives better results than just doing a delta B because it takes into account how fast you're slewing the core. So that's all in there. So the core losses go up with the voltage that you apply, even though the delta B stays the same. So we're quite comfortable about the core loss results. So the suspicion then turned to, well, maybe this Dalls AC is not good enough. Maybe it's just not good enough, and we need a better way to do that. And it's not a refined Dalls things where we shift to Bessel functions and do much more complexity for a 20% increase. We've got to find a lot more than that. We can see we've got to find, what is it, almost 1 watt of loss here, and the Dalls is only giving us 0.4. So we've got to triple the amount of losses to be able to give us a model that's going to work. So what can we do next? Well, let's see if somebody has measured the RAC. So we're going to try and build a little model here with a measured proximity value. And of course, the first place to start is with the data sheet. So this is the data sheet from Coilcraft. I'm going to move a little thing on my screen here. This is the data sheet from Coilcraft. Here's our 15 microhenry inductor. And you can see this climbing to a big value here. We'll talk about that scale in a minute. And then you can see down at the frequencies we're interested in below 1 megahertz. You can't read anything. So the winding AC resistance here that's presented from Coilcraft, it's of no use to us in looking at the data sheet because you can't read it because they plotted it on a linear scale. So that's the first problem. Second problem, and we had a big discussion about this on our Facebook group, is, well, what about these scales here? Does this really get to 1,000 ohms at 10 megahertz? And does it really get to 500 ohms at 5 megahertz? And I think we went around the whole group, and I think somebody from Coilcraft actually chimed in on the end. It's like, no, this is supposed to be milliohms. So the marketing department who prints the curves forgot to put the little m in there. Easy mistake. So I don't know. I can't attest to that, but that was our theory. But it doesn't really matter because we still can't read the series resistance here. We don't have the raw data to be able to plot it on a decent scale. So what should we do next? Let's try measuring it. So we got the AP310 analyzer. It was not originally designed to be a balanced bridge for measuring, difficult measurement. These are difficult measurements to make, and it wasn't originally designed to it, but we have come up with some test fixtures to help us here. And this is the test setup. Some of you may have the AP300, AP310. Some of you may have a Ridley box. It uses the same test setup. And we take the source from the output here. It goes through transformer isolation, which is passive. And then we establish a Kelvin connection to the inductor. And then the Kelvin leads come and hook on here to the plus and the minus. You don't want to measure the contact resistance to this part. We've got only about 2 milliohms of DC resistance. So we've got to measure a very small resistance, and we got a lot of inductance in there. So a lot of impedance is going to be, reactive here. So this is a difficult measurement to make. Lots of people ask us about this RAC. Can you get good results? Can you depend on the results? And the answer is yes and no at the same time. Okay, as we're going to see. But we've done lots of coordination versus predictions, and we're very comfortable with this measurement setup. And we've used it on many other analyzers as well. This same part got measured on HP 4194 as well, which has an impedance setup, which does the balanced bridge approach. But quite honestly, it goes a little wrong as well. And that gets us to the next part, which no one's going to like, especially in the universities. We don't publish this because, well, we'll publish it on our own sites, we'll publish it in magazines, but we'd never try to publish this in transaction because everyone's going to say, well, what's your justification? And our justification is, well, we've been doing this for 40 years. We know when the AC resistance goes wrong. So here, this curve where it starts flat around 2 milliohms, and then it climbs with a slope here. And then at some point, as you start approaching resonances in the circuit, it starts climbing much steeper. And I've seen this on so many different instruments in the past, ones that are set up as bridges and so on, that there gets a point where you don't believe the measurements anymore. These are just resonances and noise. So our approach, we know we're going to end up with a fixed slope in this. And we have many different examples of transformers, inductors, where you see this fixed slope coming in. So we just approximate this with the slope that we see here and then continue it. And this is what we call our RAC corrected. Okay, and academics out there, if you don't like it, well, that's okay. Go analyze it better. I mean, you can obsess as much as you like it, but let's do this and let's see what happens. Okay, and again, we've done this with transformers in the past, and you could see the Dalls shape coming in, you see the 1/2 slope, and then you see it going wrong once you get out towards that megahertz range. So this is our technique for dealing with this. Remember, we're shooting for practical here. So here's a comparison of the resistances that you get. This is just the 2.2 milliohms for this particular part. Here is the Dalls AC resistance, which we know when we threw it in the simulation didn't work. And then here is the measured AC resistance, which again we see coming in and climbing rapidly now at 100 kilohertz. Look how much we've increased this resistance here. It's gone from 2 milliohms to, I think, I can't remember what that was, 60 milliohms or so. Now we're bumping that up to about 120, 130 milliohms. So we've got a lot more resistance coming in here. And then at 200 kilohertz, of course, it's separated even more. And you can see the separation very nicely on the linear plot. But we can't read this down here. Same problem as the Coilcraft data that they presented. Notice here, we're not seeing 1,000 ohms, we're seeing 1 ohm. That's where we're a little suspicious. Maybe Coilcraft got it. They meant to put a milliohm in there. Okay. But I'm sure that will show up soon. Let's plot this now, because on these curves, we can't see tendencies, we can't see the power. Now let's plot it on a logarithmic scale. And this is an interesting result that we get here. On the logarithmic scale, we see, of course, the DC is just flat, fixed value. On Dalls RAC, this is predicted right out of Ridley work, solves Dalls equations for you, point by point, goes up with a slope of 1/2. And then the measured was really interesting, is that it doesn't have this 1/2 slope. It has a slope of +1. I don't know why. I'm sure somebody out there knows a little bit more. We're going to figure out where this extra AC resistance is coming from in a moment. But the slope is 1, which was quite interesting to see. So yeah, intuitively, I don't really know, but I don't care too much at this point. Somebody might be able to fill me in later on. What we do in Ridley works, and then we fitted a network to it. And that network was sort of, Weich's fractal network for him. In this case, it's a truncated fractal network of just 5 elements, R's and L's. But instead of fitting to the solution to Dalls equations, we make the measurement bring the measurement into Ridley. It fills in the values of resistances here, fills in the values of inductors. How does this network work? Well, at DC, the inductors are all shorts, so you're left with the DC resistance, and at higher frequencies, and you will start seeing these resistances in series. So you're going to get a frequency dependent resistance, and you can see that the dotted curve here is the match of the network to the actual measurements. So even though it's not following the normal Dalls of 1/2 slope, and sometimes it has a +2 slope for a while, it's quite happy to follow a +1 slope with this network in there. So that's new in Ridley Works. Those of you that already have it and have the AP or the Ridley box, it's not in there yet. It will be in there soon. So we're getting the ready that's going to include, the matching to this. Some people are talking about audio. Is audio okay there? My people here? Only a few people. All right, keep on going. All right, so here we go. Here's our measured AC resistance.
Right.
Yes.
If you remove the image of yourself on the video and just go with audio and your presentation screen, I think you can solve it.
Yeah, I'll plug in a Wi-Fi cable too. Hopefully that won't mess anything up. Sorry about this, everybody. Okay. And I will turn off my camera for a moment. I'll turn the camera back on when we get back to questions again, okay? All right, so here we are. You know what, I'm gonna leave that camera on. If everybody's having problems after I've connected the cable, just let me know. So here's our final circuit for simulation. Here is the AC resistance, which is now the measured RAC. Here's our core loss model. Here is the inductor value. And here's all the values that are passed over from Ridley Works to the LTspice model. So you can see you've got to come up with 5 values of resistance and 5 values of inductance. For the AC winding loss, all right, glad to hear that the sound and video is good now. Sorry about that, should have done that to start with, but always something. Inductor core loss model, we have a 6th order model for the core loss that we needed. Again, 6 elements here, 6 elements here. There's a non-linear element here representing the delta P to something more than delta P squared. So that all goes in. Everything here is generated automatically. Trust me, if you have to generate these models by hand, some of you might want to do this yourself, and you have to type it into LTspice when you get over there, you're going to do it once and then you're going to stop because it's too hard. So automating this is a big, big step for us. All right. Let's run the simulation. Now you see what's in here. You got 5 inductors in the R, you got 6 inductors in the core loss. Let's see if it'll run. So here's our LTspice model, core loss model, proximity loss model, and then you just click run. And then let's look at our current. Here's our current through the inductor, going through startup, and it's coming into regulation. Those of you familiar with running the LTspice, you'll know this is actually a pretty good simulation speed for 200 kilohertz, especially when we consider that we've inserted 11 inductors in the magnetics models. It should slow it down more than it does, but it's quite happy. How do we get the losses now? Well, those of you familiar with LTspice, you hold the Alt key and you click on the part, and it gives you the instantaneous dissipation. Zoom in to steady state, and there's the losses in the DC resistance, 200 milliwatts in this case. Now let's look at the losses in the core. Right there. There's our core losses, strange waveforms. I can zoom in a bit so you can see them, but they don't really mean a lot to you. But now we hold Control key and click on that waveform, And we see we've got 400 milliwatts in the core. Okay, this is so nice to be able to get this core loss without going to a core loss chart. I mean, how archaic is it that we have to run a simulation, figure out the delta B, figure out the frequency, go to a core loss chart, look it up, find out the rules to get this. I mean, this is what we want to do. We want to run the simulation, look at the core loss. Done, easy. And now we're going to look at the loss in the AC resistance, which is here. And we see we had 200 milliwatts DC. Here's our extra loss, 1.14 watts in the AC resistance. Now we're starting to look like we're getting somewhere close to what we want to have. So this is good. We've got core, measured AC, DC resistance. All is coming together, I think, at this point. And this is fun. I don't know about you, but I like running SPICE simulations and getting results like this. Go back to the slide. This is the slide that you have. So here are the individual losses. This is the DCR, 200 milliwatts. Here's the core loss, 400 milliwatts. And then here's the ACR losses, 1.15. So 7 times as much losses in the windings as you see from a DC calculation. Okay, so obviously we really want to fix that. There's the final results versus the Coilcraft measured results, or their DC to DC optimized. It's pretty close now, right in the middle. 110 volts input, the nominal voltage input. It's right on top here, and we give a little bit more dissipation at high line. We get a little bit less dissipation at low line. And same thing with the changing frequency. We predict a little bit more losses than theirs does, and then a little bit less losses to here down at the lowest frequency. But to be honest, you're not going to move away very much from the 200 kilohertz. This is nice to have, but you know, this is the point that we're looking for. So why did we miss a little bit? Well, to be honest, we don't know which material they're using in this inductor. We can only guess at it because one of the modern trends of the magnetics manufacturers is to not tell you anything about the design. So certainly they're not going to tell you the core material. So then you say, well, how do I do worst case analysis on this part? It's like, well, you can't. You can't. There is no worst case analysis. If you don't know the core material in there, then you really don't have a hope at getting to the results, the worst case results. Also, unless you count them, which we can do here on this inductor, you know, nothing in the data sheet tells you the number of turns or the core area. So all the other aspects of worst case analysis, you know, well, am I getting above 0.3 Tesla, which is a no-no for many companies? You can't even assess it because, again, a modern trend these days is for the people who make off-the-shelf magnetics. They don't want to tell you how many turns they've got. So hopefully they'll change that. If you push, they'll tell you. If they won't tell you, you just take them apart and count them. It can be a little difficult when you got 140 turns, but you know, you can get that done. Okay, I'm happy with these. So the question is, are you happy? Are you going to start using these models? We'll see. The only people that are going to use these models, to be honest, are people with Ridley works, because it's too hard otherwise. You can go derive it yourself. You're going to put so much work into it. You say, you know what? It's easy to use everybody's program. But now, of course, when you use the Coilcraft DC to DC optimizer, they've only got it in 1 or 2 topologies. Buck boost, maybe a buck boost. If you put this inductor into an LLC converter, you're on your own. But with our model, we can now take this LTspice model of that inductor. You can put it in any topology you like, and you will get a good prediction of what the dissipations are going to be. So it doesn't have to stay within the domain that's being characterized. We want a circuit model that we can lift and put it into any circuit. Where does the extra RAC come from? Pretty sure it's the gap. So you look at this structure here. Okay, you can see, is my camera on? I think my camera's on. Yeah, my camera's on. Hopefully you can see it. You can see the structure here, and we actually dissected one of these and we pulled out the windings, and we were able to get a measurement of the gap in here. Now, of course, the only way you can dissect these things is you break them apart. And when you break them apart, of course, you can't measure the gap anymore. You can only measure what's left. Okay, so you have to measure this dimension and that dimension and that dimension. Hopefully you haven't broken the whole thing apart. And then you can get to the gap approximation. And we had a backup on this to confirm that that was approximately correct, because in Ridley Works, we put the same core into the structure and it told us, yeah, this is going to be about a 0.5 millimeter gap in. So that's about what we measured on the part. And then we find that the windings are very close to the gap, which of course is what you're not supposed to do. Okay, way back from the beginning of power electronics, it's like if you have a gap, don't put the copper near the gap. So we've been talking about this 30, 40 years, about get the windings away from the gap. Universities now are talking about, well, let's make the gap distributed so it's smaller. Better idea is don't use an EE core here, put that gap at the top and then move the windings away from it. And that's my approach. I mean, Rudy Severance gave us the rule many, many years ago. You just put the copper 3 gap distances away, and then you don't have any significant gap loss. So my approach is let's build it properly, and then we don't have gap loss, and then we don't have to do the analysis of the gap loss. But if you can't avoid it, or if you're using a standard part that we're looking at here, measure the AC resistance, and then that, as we can see, is going to give us a very good approximation to these losses. Okay. There we are. So it's much more relaxed this time than my usual webinars because I don't have equations in there. I'm trying to put concepts across here, and I'm not trying to run too much software. I wanted to leave plenty of times here to go look at your questions, but also steer you to other things to read. The winding loss here, we have a full 1-hour webinar on the winding loss. So you can see how Ridley Works deals with that. I think I even give some of the equations there. But it's not doing you a favor by giving the equations, because then you've got to go program them. So I don't encourage you really to do that unless it's something that you love doing in your spare time. Second reference here is the magnetics core loss. This link will take you to the core loss webinar, how we build up the core loss model. Okay. Take a look at that. Let me know what you think of it. The purists, the academics out there, they won't like my core loss model, but that's okay. I haven't seen anything working any better yet. Coilcraft DC to DC optimizer is here. And then people who want to dig a little bit deeper is for our proximity loss modeling and the modeling with a fractal network to match the eddy current losses or the proximity losses. This was first done way back in 1993 in this paper, and I've seen at least 2 other people doing the same thing in industry. Not many are doing it, but other people are starting to do this. They're building up this proximity loss model here with RAC using the R's and L's. So this is almost becoming common practice now, which means that more than 3 people have done it. Okay, I hope everybody starts to do this because it's not hard and it's very powerful when you start doing this. Okay, so there's that. Extra learning material. Okay, I'd like to thank Jimmy Daniel, who's on our Facebook group, who did a bunch of the simulations for us. He has a copy of Ridley Works, and he did a bunch of filling out of the tables. So thanks, Jimmy, if you're out there. If you're not, thanks anyway. Okay, that's what we got. And we're going to give you 1 extra page to look at, and then I'm going to answer questions, because the big question is, I don't have Ridley Works. My boss won't give me a budget to get Ridley Works because he says I've got LTspice and that's free. So why should I spend more money? Well, you can get Ridley Works for free now. We're going to be holding a one-day power design workshop, Saturday, February 24th. We did these quite a few years ago around the world in different places, one-day workshop, and as part of the workshop, you get Ridley Works, okay? So hopefully this comes out your education budget. People have those, and you will get your Ridley Works. So registration is the exact same price as 1 year of Ridley Works. So once you sign up for this workshop, and the links are live now, we will send you your link to Ridley Works. So it lasts for a full year. So you can get the Ridley Works now, and then in February, of course, you know, you'll be very familiar with using it. You'll have questions and so on. But if you like, you can go sign up for this workshop immediately. There is going to be limited spaces for the in-person, okay? We're going to have a remote attendance as well for people that are overseas. So this is how you can get your copy of Ridley Works for this. All right, let me pull out the questions here. Let's see where we are. Gosh, lots of questions. So. Thank you. The blue line, so the blue line, somebody's talking about the DC losses in the charts. Is it measured with a digital multimeter? Well, we do it with that, but we also do it with a frequency response analyzer because we're accurate down to below 1 milliohm with that, and we can calibrate even better than that. But yeah, DCR is fine for that. DC to DC optimizer from Sophia Hart, that's Coilcraft's program. So just click on the link that's in your PDF and it will take you to their design page. So is it a simulation tool? No, it's a calculation tool. They don't, none of the vendors have simulation tools. They give you canned waveforms and skew them up and down, but they don't do true simulation. We do simulation inside Ridley Works. Okay, it's a true simulator in there. It's much, much faster than anything else you can get. So you'll have simulation there. Plus, of course, we'll have the LTspice models. So let me. Okay, actual measurements are taken. I think we've answered that. We've shown you the setup there. You do need a good frequency response analyzer that can resolve well, and you do need an impedance test kit for doing that. So we have that available for people. And of course, we have the frequency response analyzers. All right. Do we use the frequency components of the current waveforms versus RAC? Yeah, LTspice does that naturally. You put in RAC as the LTspice model, and it naturally is decomposing into all the harmonics, multiplying I squared R for all of those, and finding the solution. That's the beauty of these LTspice models that you build. You can't do that analytically. You can't extract all those harmonics easily. And then multiply every RAC, which is the solution to Dalls equations, or in our case, of course, it's measurements. So there you go. Why are the losses increasing with the speed of changing B? Is this not switching frequency? Yeah, we're increasing with changing switching frequencies. But I think if you look on the curve, you'll see that losses decrease with frequency and increase as the frequency goes down. Now, the AC resistance, of course, is climbing with frequency. That's just proximity loss, and that's the gap loss. Thevenin connection, that means you have 4 terminals. You're testing, you're driving in a test signal, but then you're connecting on the right side of the connector. So you're going right onto the lead. So none of that test signal is going through the measurement. So that's what lets you measure the very low resistances. What voltage levels do we measure RAC? We typically use 1 volt test signal. It's 1 volt with 50 ohms. We can drive it with a power analyzer as well, but you find it's not that variable with the test signal, but you can try different levels. But 1 volt is typical for us. Modeling a saturated inductor in LTspice. Well, I work on circuits where we don't saturate the inductor. Most of my customers don't want to saturate the inductor because that's going to lead to failures. I haven't always done that. My very first power electronic circuit was with a saturating inductor. We put a switch value of inductor in there, we could get some of that. But while it's interesting, for maybe 0.1% of the industry, it's actually useful. So yeah, absolutely. If you want to go model a saturated inductor, put that in there if you want to. But it's not the bulk of the marketplace. Does Dalls' equation assume a cylinder? Yes, it does. Oh, just a curve, a note on calculating the gap loss. You can put that gap and the turns into a piece of finite element software, but you're going to have a devil of a time describing it because the turns spiral up around a single turn. By the time it's gone around a turn, it's gone more than one gap away. So at every little point around that circumference, it's a different distance from the gap. So you got to do a really good three-dimensional model around there to get that. That's why, you know, always in our field, well, do we analyze forever, or do we go measure it and see what we've got and don't worry about the analysis? If you're trying to write a paper for the IEEE, of course you're going to analyze. If you're trying to get on with the work, you know, you're not. Okay, when do we have a webinar on saturating inductors? We don't. Maybe if I had nothing else to do. If everybody goes out there and we have 1,000 people signed up for our teaching event next February, we'll take some time and do a saturated inductor, but it's not really interesting to me. Again, in this field, you shouldn't be saturating your inductances. I know in motor drives, they do saturate a little bit. It's more important to them, but it's not important in general for the power electronics community. Somebody said slide 14 is interesting. I can't see a wild, seen a wild curve like that. Let's see if I can find that. Slide 14. Yeah. Well, you know, wild curve, I assume you're talking about the whipping around here. You know, the reason this is a hard measurement to make is because we're trying to measure 2 milliohms, and we got lots of inductive impedance in here. So it gets very, very hard to extract that DC part from the AC part, and that's why it thrashes around like that. When you see a lot of the papers, I'm pretty sure in their process they generate curves like this too. So they deliberately wind an inductor to prove proof of concept that has like 100 milliohms resistance, and then it doesn't do this. So if you've got an artificially bad inductor to look at, then you know you get much cleaner measurements. So yeah, so there you go. There's a curve in the wild. So I've seen this for 40 years. I've been measuring curves like this. That's why I know, hey, let's correct it. The +1 slope was interesting to me. I'm gonna have to dig a little deeper, maybe read a little more. I'll wait for one of you to tell me why this is a +1 slope and not +1/2, which is what we normally expect. Okay. All right, saturated inductor, layer. Slide 14, ladder model, okay. For module fitting, what about phase shift introduced? Well, we run this ladder model in our simulations all the time. In fact, we've even done things where we've done the small signal of the buck converter with core loss and with AC resistance loss. We do a sweep in LTspice, or you can do it in the average models. So you can actually find the effect of proximity loss and core loss on the transfer functions, which is really interesting because nobody's ever written a paper about doing that mathematically. You can only do it in the models. So yeah, that's a really nice advantage of this approach. Once you've got these circuits, you can do all your AC analysis and your DC analysis. And some of the original paper did that. It was for stability of a very high power system. Okay, does Ridley Works use Volparian's PWM switch model for simulations? Well, it uses it for simulation of the loop. However, it cycle by cycle in Ridley Works is cycle by cycle. It's simulating the switch as you go. It does it about 100 times faster than LTspice will, because we've got our own simulation algorithm in there. If we're modeling an AC inductor, permeability of the materials changes in the BH curves. Well, if you've got a gapped inductor, it's not going to change with frequency. It's a pretty fixed value of the, I mean, the permeability, the inductance is set by the gap. So it's going to be linear. It's going to be fixed with frequency. Coupled inductors, haven't done those. Do they work for transformers? Yes, that's where we started. We have a paper, we haven't published it actually, but you will find in our webinar on proximity loss that we did transformers in there. And we did them, and then we did thermal measurements, we did actual losses, so we confirmed that originally for transformers. Moving on to inductors with this very low resistance was a challenge, so this came later. Somebody missed where we entered the core specs in the model. That's in our webinar on core losses. So go look at that. We'll show you how you do that. Same thing, inputs to Ridley works. Go look at those older models. Can I point on the actual picture where the gap is? Well, it's there. The two core faces coming together. Okay, it's just 0.5 millimeter separating the two. So quite a small gap. How do we enter the measured RAC into Ridley works? You need the next version. Not quite available yet, because we've just been doing this stuff. Can Ridley works be imported into other simulation packages? Well, why did we start with LTspice? Because LTspice is the most prolific out there. Do we work with Simplest? No. Could Simplest read a Spice model, LTspice model? Well, if it can, it should. You know, they need to work on that because everybody's LTspice. You know, we're not going to put out very specific Simplest models. We do put out PSIM models, but quite honestly, we should all be starting with an LTspice, and it should be able to be read by all these packages. And some of them do, I think, now. So, you know, if you got the LTspice model, you can take it and put it into any of your favorite simulators. Same approach for powder core, same approach for powder core, absolutely. Any plans of a workshop in Detroit area? Well, let's see how California goes. Hopefully there's going to be a lot of people around California at that time, and that works out well. And then we are considering taking this elsewhere around the world. Detroit, I'm not sure. We'll see. Parameters extracted from measurements. That's automated in our software. Does the Ridley box use square voltages? No, it uses sine waves. Everybody uses sine waves. All the test data for the core material is a sine wave. However, the model for core loss can take the sine wave data, and then you can apply a square wave to it, and you can watch the dissipation change. All right, so it doesn't care what the waveform is. It can be a sine wave, it can be any waveform you like. And of course, normally it's a modified square wave driving it, which is a modified triangle wave in the current and the delta B. Do you see ChatGPT taking work away from power electronics designers? Well, the ones that aren't very good at their job, sure. It can fake it, but it's not going to debug a circuit for you. Can you use this model in PSpice? You've got the LTspice model, translate it. We're not going to do that for you, okay? Again, everybody should be centering on LTspice because everybody has it. And then, you know, translate it yourself, or hopefully they provide a feature in there where they can read LTspice models. Distributed gap, would that help? Yes, it would, because the gap would be smaller, and then the core, the windings are further away from the gap in terms of gap distance. So that's good. LTspice is used because it's cheap? No, it's used because it's good. Okay. Why pay for Ridley Works software? Just use a bootleg version. I can't believe somebody said that. Well, if you're using a bootleg version of Ridley Works and you know about it, please let us know. You know, if somebody's bootlegging the software, then webinars like this aren't going to happen. So, you know, let's be honest out there. I know it probably happens, but we haven't seen a lot of examples of that yet. And of course, you don't get updated if you got the bootleg version. But thanks. Parasitic elements like capacitance, look, if we can't get the manufacturers to do AC resistance, there's no point doing capacitance. There's just no point. Can we put a capacitor across it? Yeah, you put a capacitor across it. So it's just not, it's not an issue. But for years now, we've been talking to everybody, let's do the AC resistance, let's do the AC resistance. The pushback so far from magnetics industry is, no, we're not going to do better SPICE models. We're going to do our own special programs, which aren't that much help to us, okay? And I can see why they've done that, because the AC models haven't worked that well. But now that we're measuring them, we're getting good results. Let's start using them. And if you want capacitances, we'll add the capacitances in there. It's quite easy to do. Would our AC increase with slope greater than 1 if the gap was larger? I don't know. I don't know. It's the first time I've seen that +1 slope. So interesting to me. Why don't you use Mad Mix? I don't know what Mad Mix is. I'm done with using different pieces of software. I like to build circuits, get them together, estimate, do it. Mad Mix is not going to speed me up. It's going to slow me down. I've got a whole new interface to learn. So I don't even know what it is yet. I have to look it up first. Let's see. LTspice is elegant. LTspice is also expensive. Lots of companies, spacecraft and other, use LTspice. Lots of people use LTspice. Lots of people use Simplest. They're fragmented all over the place. So just read the LTspice models and it'll be easy. AC resistance, blah, blah, blah. If I had measured the RAC with a winding extractor from the core, good question, would I have the same core? My intuition is the core is not making any difference. If it was making a difference, the AC resistance would change a lot with the excitation, and it doesn't. So I don't think winding a core loss is getting. Have you considered your licensing our modeling techniques to other vendors like Simplest? Well, I would, but they're not going to pay for it. It's just a fact. All right, I will attend your workshop at Long Beach. Thank you. We try to be valuable in our lectures, so please, yeah, we expect it's going to be quite popular. Last time we did this, we had 400 people in the room. We don't have room for that many in February, so if you want to be there, and of course, once you sign up, you got software, so you'll enjoy that. Have I measured the winding without the core? Yes. Is the AC closer to Dalls? Yes. Does it mean anything? Just that it's the core gap that's causing the. We've also done it with cores without gap for transformers, and then the Dalls, and then the core loss present, core present or not present. There's not much different. It's only bad in this case because the gap is in the wrong place, quite honestly. Should they redesign this inductor? No, they're probably selling plenty of them. You know, could it be lower loss? Sure, but if you're not going to drive it, most people with as much ripple as us. So does it matter? I don't know. Only they can answer that at Coilcraft. Do they sell lots of these parts? Do they make plenty of money? Keep doing what you're doing. If you want to try moving the gap somewhere else, try that too. I would love to do that if I had time, but of course this isn't easy. Getting that same core with the gap moved down the end, it's a tough step. How many parts have we modeled? Hundreds. And lots of our users are starting to study doing this too. LTspice agreement limits its use for product development purposes. Haha. You think anybody pays any attention to that license agreement? No, they don't. The license agreement says you shouldn't use it for somebody else's part, but everybody is. Last I heard, LTspice was getting 100,000 downloads per month. So it's an unstoppable machine. It may not be the best simulator, but it's so widespread. Every one of us can talk to each other with an LTspice model. And that is really important for many companies. You cannot afford to buy PSpice for your group of 50 engineers. It's just ridiculously expensive, but they can all have LTspice. So that's hugely important. And are people using it for product development? Of course they are. What else would you use? Great if I came to Texas. Well, try to get to California. It's nice here, especially in February. Come on to California, it'll be kind of fun. Better result if the gap is through the different legs. So if you gap across all 3 legs, the gap is approximately 1/2. Is it better? Yes, it is. We do that quite a bit. Anything you do to shrink The gap size is a good thing. Do we have an issue with PSIM compared to LTspice? Yeah, my PSIM of course runs really fast, but I don't know, I'm at a stage of my career where I don't want it always to go that fast because I need to think about what my circuit's doing as it's doing it. So speed of LTspice now is sufficient. And it really comes down to the control chip. How complex are you making that control chip model? We don't want transistor level control chips in our models. So we have behavioral models. So when you do that, you know, LTspice is just fine. There's, you know, but PSIM is nice that it will give you that blazing speed. So for large systems, yeah, motor drives, things like that, yeah, it's really nice to have it. My issues with PSIM are the interface is a bit tough. If I want the power in a component, I've got to put a voltmeter and a current meter across that one component, which is really inconvenient. I'm sure they'll fix that eventually. But it's a nice program, which is why we link with it. Okay, younger generation colleague will certainly go to magnetic seminar in Long Beach. Yep, we'll see. We have magnetics in there. We have other topics as well. We're not going to do just magnetics. Excited to see how we'll model the transformer. We've done that. We tried to publish it and we didn't publish it, but we've been sitting on that paper for 5 years, so we will publish that. Maybe we'll have a webinar on the transformer models as well. Do the core losses affect the measurement? No, I don't think so. That's, you know, we can debate that all you like, but hey, I messages what's coming out of the manufacturer's data sheet. What more do we want? Can we split it into this and that and this and that? Sure, do what you like, but we want a model that works, and that was our goal. Doesn't the fringing effect? Yes, the fringing effect is manufacturing an RAC. Absolutely. That's why the core is in there. Can you model the fringing effect of the gap? Sure. If you got nothing else to do for 6 months, model the fringing effect in the gap and write some equations and run some simulations of that, or measure the RAC. Is this workshop different from the ones we've done in the past? Absolutely, it will be different. We always do something different because the industry is always changing, always changing. So there's always new things to talk about, especially in the topologies area. Lots of things are happening there. People are struggling to keep up. What am I supposed to be designing? You know, if you listen to some people in this field, they'll tell you the buck and the boost and the flyback died a long time ago. If you look at the industry, the buck and the boost and the flyback are the mainstays of the industry. Some people will tell you should be doing dual active bridge. Some people will tell you you'll be doing LLCs. Some people will tell you should be doing phase shifted full bridge or hard switch full bridges. So many topologies now that it's impossible to sift through. That's what we're going to talk about with the topologies. They've all got one thing in common. I'm not going to tell you that until we get to the seminar. But they've all got one thing in common. They're all heading in the same direction. They just don't quite know that yet. Daniel Trambita says, I'm talking about the upcoming one in February. Where's your first question? Can't find it. Oh, is it different from the ones you didn't pass? Yes, it's different. It's different. It's a new seminar. We always put new stuff. I don't like to stay stagnant on any of these things. You know, I get bored presenting, people get bored listening. Manual. If I have any leftover lemons from my trees, I'd be interested. I have no idea what that means. We have limes. Can you provide a simple, complete transformer model template? Okay, if you got Ridley Works, you've got the template. It's going to output. Demo software. Okay, I don't know what you mean by demo software. When you come to this workshop, you get the full version of the software. To be honest, our demo software are always way out of date on those. I mean, we're just so busy pushing forward on the real software that the demo software is normally at least 2 generations away from where we are. Okay, somebody asked limes. Again, I don't know why you have any questions about that, but interesting. Okay, I think I've covered all the questions. Thank you for the webinar. Well, thank you all for coming